Good evening, students. I'll start with the class. In the previous class, we had seen equilibrium of a body. So there what we had seen that there's pure one, okay, that is the static equilibrium when both rotational as well as translational. Okay, this is what the body with both translation as well as rotational is at looks like it is at rest only. The forcing acting upon it would be zero. So here torque total net is zero. Here total force is zero. Torque is nothing but a way of writing force in rotational motion, and force is in terms of linear motion. Next one we'll see what is couple of forces, also called as a couple only. So it's a pair of equal and opposite forces. Best option is best example is when you want to open the cap of a bottle. Okay, go and try to open it with a one finger. It will be difficult. Okay, the bottle cap is quite tight enough. You will need both the sides. Okay, force in order to open the cap. So it's a pair of equal and opposite forces with a different line of action. Results in a rotational motion. So here are some examples. Yeah. Okay. A couple is what? Equal and opposite forces. So if you want to, when you're driving a car, a wheel, if you want to spin or rotate, so even though you may not apply, but exactly some force is there. Okay. This wheel is moving, spinning. So one force, one direction of the force is upwards, the other side it is coming down. You want to open the knob of a door, so it's a pair of equal and opposite forces. The thumb is applying force on in the clockwise direction, and the pointing finger may be applying force in the this other way around. It looks like one is going upward, the other one is coming downward. Same way for tap also, opening a bottle cap. These are the basic examples. You can write. Opening the cap of a bottle is understood. One is enough. If you want, and the steering of a car. Third one is tap. Okay, opening a tap. Okay, so this is a couple which needs a set of two forces. And see what is the principle of moment of a lever. Consider like a seesaw in a park. Okay, let's say example, maybe you are placing somewhere the, so this is a fixed point at which it is attached to. About this it will move, either this part will go up or this part will go down. So this part is called as a fulcrum. Okay, you can just write and keep example. Seesaw in a park. Let's show you some more examples then. Now one person must be sitting here. When the one person is sitting here, must be applying some force this side. You can consider this side F1, the other side to be F2. The other person is sitting here, so the other side is F1. Always at the fixed point, there will be equal and opposite reaction to balance these forces. So there will be some weight here, some weight here. So that weight will be downwards. So there will be some this force created at the fixed point. Otherwise, what it will never remain here. It will fall on the ground. Okay, so there's some force, opposite force, which is trying to balance this. So on this fulcrum. So let this distance be d1 and let this distance be d2. So for translational motion, for linear motion, normal motion, always the forces F1 plus F2 will always be equals to R. Downward forces are always equals to upward forces. Okay, so this, if you take on the other side, R minus F1 minus F2 should be equals to 0. This is for translation motion. And for rotational motion, if in case this was spinning around, this is what either coming up or coming down when you seesaw. Now imagine this was what? Round. Imagine the seesaw could rotate also. So for rotational motion, okay, imagine someone is sitting here. So this is spinning. If I give a force like this, that person will take a round like this and come. You can imagine this saw moving. So if it was like that for rotational motion, this distance d1 f1, because it always matters with the distance from the point of the force, will be equals to d2 f. This force will always balance out with this at equilibrium. Okay, now this f1 Suppose the person is sitting here, means considering the load is here now. This is your main reference load. So F1 will be considered as the load. Okay. And this D1 will be considered as the load arm. Now a person went and sat here. This is load and this is the load arm. Now you have to put some effort to balance this. Because now someone has to come and balance this. So F2 will be called as effort. And same way D2 will be called as the effort arm. Okay, so there is always a fixed point called as a fulcrum. One side will be the load and next side will be always the effort. I'll just share the slide and give you some examples. Okay, so these are like the various day-to-day life examples. Fulcrum is always the fixed point. One side will be the load. The other side where they mention force is always the effort. So you have to put the effort to bring that load up. First, in that class 1 is what you have to put a downward force to bring that load up. Here, what is happening in the second, in that class 2, even if you try to put that force downwards, definitely that plank will fall on the ground. So now you have to apply some force to keep that load up only. The force will be upward. That load is at the end. These are the various examples where you could have a combination of fulcrum. Instead of force, it is effort. Okay. Now, applications, day-to-day life. When you use a hammer to remove the nail, so that is your load at the end. That is the nail which you want to remove. Now you have to keep it fixed. You must have noticed simply in the air you will not be able to remove that nail. So you have to keep that F is the fulcrum fixed point and then put some force and the handle of the hammer. That is the effort. These are not there asked in the textbook or something, just to show or to understand what is the difference between fulcrum, load, and the effort. Fulcrum is the fixed point. Load is the one which you need to work on, and how much force you want to apply to make that work done. That is the effort. So as per this, it is always what is D1? D1 is nothing but the load arm into load will always be equals to effort arm into effort. This into this should be equals to this into this. Okay, there's a word called as mechanical advantage. It is nothing but the ratio. Mechanical advantage is always the ratio. This upon this side upon this side. F1 upon F2 is always equals to D1 upon D2. D2 upon D1. Okay, F1, this is brought here, this is brought here. So that value is called as a mechanical advantage. If in case mechanical advantage is greater than 1, more than 1 means what? When will you get this value 1 compared to this? Just see this. Considering this, when you'll get this 1, whenever this number is bigger than this, 5 divided by 4 will be 1 point something. But if you have 4 divided by 5, it will be 0 point something. So when the numerator number is smaller than the denominator, it will be less than 1. Okay. So when is greater than 1? When numerator is greater than the denominator. What does this mean? This means larger the load, less will be the effort. And if mechanical advantage is less than 1, it means this number is smaller than this. So it means less load, larger or small load you can. So if you ask what is the principle of this, this is the main principle of a lever. So this was about the moment of a lever. Next is something called a center of gravity. I'll share one image and you'll be able to understand it better. Okay, consider whenever this balancing thing happens, there'll be so many cases. People try to spin the cardboard. What is that? That book on the fingertip. Sometimes the football on the fingertip. Must have noticed. Even on the head, sometimes you try to balance. All these balancing effects which take place in the real life, what plays a major role is the center of gravity. Okay, why is it to be able? Now look at this picture itself. The pencil is there on the fingertip. It is not falling. Why is it so? It is because the finger is exactly at the center of gravity. If imagine you shift that finger slightly on either of the side, it's able to understand better because it's the lengthwise. I know it's exactly at the center. Even if you try to shift even a small this, you will not be able to balance the pencil, it will fall down. Why? Because you would be shifting the finger away from the center of gravity. So it's like how it's like dodging the gravity of Earth. You're trying to just not necessary it has to be lengthwise. Some people can, it's a box, and on the tip of the this also you can just hold this box at the edge. Okay. Sometimes you must have seen those eagles and all, which you can just balance at the tip of the beak of the eagle. Okay, like this. Must have seen those toys. I think there's something like this. And then there's an eagle which is balancing itself. Okay, like this. Why? Because this is balanced at the center of gravity of this particular thing must be at the beak. So not necessary it has to be there only exactly between this and this. If it's like this, it could be somewhere here. So when you balance it, it lies the point of center of gravity lies in that particular direction. So what is center of gravity? Center of gravity of a body is that point where the total gravitational force, torque, you can say, torque acting on that body is zero. Okay, imagine on a fingertip you are trying to spin this disc. Okay, there's a disc which is spinning on this point. Why is it happening so? Because the total now the gravitational force is always there towards the ground. Okay, but what is happening at this point? All the force total, when you try to balance on all the sides, at this point it is zero. If it is not zero, means somewhere it will be heavy. Heavier means it will fall down. Okay, the center of gravity of a body is that point where the total gravitational torque, okay, for rotational motion we use the letter torque, use the word torque. When it is spinning, that force on the body is zero. So for equilibrium, and this is at equilibrium, what is going to happen? There's a weight for the disk, so that is mg, which is acting downwards. But why is it at equilibrium? Because there's a opposite force which is called as a reaction. This is the reaction. They are balancing each other. So for equilibrium, R should be equals to your weight. Now this M I'll use capital. Now since we are doing the center of force, no? So basically, if you use the system of particles, these are all small masses. M1, M2, M3, M4. Okay, basically all the masses combined together. So this is used as a center of mass. M. So this M is nothing but sum of all the small particles. So that's why it is a capital M. So what is this? Nothing but sum of all the small particles. These are the particles. The total force, net force acting on that disk will be zero at equilibrium. This is for translational. If this is moving this side straight, if it is spinning, then it is, this means that this disk is balanced. If this torque was not zero, suppose, then not balanced, disk would fall. Then the disk will fall down. This total net force, again, this total torque balances the gravitational force. Okay, it balances the total gravitational pull, therefore called as gravitational torque. the torque is nothing but all the forces which are coming towards this. Okay, this point is balanced by all the forces which is trying to pull it down. So that's why the word is used as gravitational torque. Note, this is very important to know. Center of gravity of a body coincides with the center of mass. The center of gravity point will always lie the center of mass. They will not be at two different places, because then what is going to happen, one side the mass will be this, it is not possible. Imagine this is here. Now consider you are having a center of mass here. It's always understood. For symmetrical bodies, it is always at the center. This is your center of mass. But if you are claiming that your center of gravity is here and try to keep your finger, even practical logic wise thinking, it's obviously understood. If you keep your finger here, center of mass is here, so it is heavier this side. It's like this mass is concentrated here, so it will fall. Okay. The center of gravity should always coincide with the center of mass. Wherever there is center of mass, that is the point where you have to balance, where the gravitational forces acting on it would be zero. So we'll prove it also. Okay, this is gravitational torque. It's a sum of all the torques coming together. Okay, this is a particle, no? All the particles, we know that they are all like acting on the center of mass. So this is torque 1, torque 2, torque 3 due to every particle, and that normally we use as net. Instead of net, we'll use the word letter I. I means 1, 2, 3 like that. Just changes sum of all the torques. So you know that torque is nothing but, what is the formula for torque? R into perpendicular force. RF sine theta, we have seen that in the previous class. Torque is nothing but R into force, the radius into force, the perpendicular force in terms of vector. When you remove, it is always RF sine theta. So if it is perpendicular, sine 90 it will be. So torque is always R into F. If it's a 90-degree force. So as per that, what it will be? Ri, all the radiuses of all the this particle into F. Force is nothing but mass into gravity. F is nothing but mg. So just use I and I for both the places, because these are we are referring to all the set of particles. G is always a constant. It is common to everyone. Gravity for this particle and this particle will be same. So G I'll remove out. What is distance into mass? We have always seen x1 m1, x2 m2 is always nothing but what? Center of mass. So this is nothing but center of mass. So if torque is 0, if this is 0, that means this is also 0. So if both are 0, means they are equal. So then torque, the gravitational point and center of mass is same. that is center of mass is also equal to 0. Means it is at the same point. We are talking about the same point. They coincide. So this was about center of gravity. Next we'll see what is moment of inertia. Use the word I. I is for inertia. Definition wise, just write the definition first. Then I'll explain. Moment of inertia of a body about a given axis of rotation is defined as the sum of the product of the mass of each particle. While writing, you will not understand anything. Once I give the formula, you'll be able to read this properly. It should make sense. And the particle in the square of its distance from the axis of rotation. Let's write this in a diagram and explain. Consider there's one fixed axis, okay, and there's a small mass at a distance r, suppose from here. This is a small mass, piece of mass, which is at a distance. Now imagine I'm applying some force here, and it will start spinning. Okay, from here it's revolving around the axis. Imagine like there's a ceiling fan only, you can consider. At the edge of the fan, okay, imagine this was a fan. At the edge, you have just applied some mass. I'm considering this mass at the edge. So just imagine how that mass would be revolving around the fixed axis of the fan. Okay, in 2D the diagram becomes difficult to imagine, but this is at a far distance and moving around a fixed axis. The fan itself is an example. You can think the wing, at the end of the wing you have attached something, and then you're applying some force to the wing. You're just giving it a push, so it will be rotating, spinning around the main axis. So I can say that the moment of inertia across this axis, suppose A and B. So moment of inertia along AB, IAB is equals to mr square. So this is the definition. Mass into the square of the distance from here to the main axis. Now refer this and try to read this. Moment of inertia of a given, okay, of a body. This is the body about a given axis. So this is your axis, is defined as, okay, this sum I'll explain. Now as of now just ignore the sum because I am referring it with just one mass. I'm just taking it as m1. Okay, just ignore this word sum. The product of the mass of each particle, means one particle only I am taken now. This is for one particle. So if there are many particles, you'll have to add all those. That's why the word sum is there. The product of the, one second. It's too much of disturbance sometimes. Okay, so this is with reference. So product of the mass of each particle and the square of the distance. Distance is nothing but radius. Square of distance means r. So r square, distance from the, this is to, so right, m is the mass of the particle and r is nothing but the distance from the axis of rotation. This is called axis of rotation. So this is with reference to one particle. Now imagine like this, we have many particles. Okay, now this is what at the wing of the fan, only one point. Imagine the whole wing, we consider many points. So now the what I'll give the actual formula is for system of all the particles. So this is the axis of rotation. If suppose this is the body which is rotating along this, different masses are there, m1, then you can consider m2. So this is spinning. Okay, spinning along this. This is m3. So these are with reference to one particular point. It would be with the center of mass. This would be r2. This would be, which one I use, m1. This will be r1. This will be r3. This is with reference to origin. And like that, maybe many. So this would be mn. This would be r into r of n. So moment of inertia for all the masses will be what? m1 r1 square. This is for the first particle. This is for system of particles. m2 r2 square, m3 r3 square, and so on till the last particle. So that's why the word sum was there. The sum of all the masses, sum of the product of the mass and the square of the distance. So in general, what we can write is summation sign. Only what is changing, these numbers are changing. The subscript is changing, but m and r square is remaining the same. Only these are changing, no? So that we generalize it with some letter I, because I will go from 1, 2, 3, up till n. I is going from 1 to n. Either you write it here like this, I can write it the side. I is from 1 to n, starting with 1, ending with n. So this is moment of inertia, actual formula that I had given only with reference to one particle. But if asked what is moment of inertia, this is the main. We'll see more in detail about this moment of inertia. Unit is kg meter square. Why? Mass is kg, distance is what? Meters, and there's a square. This is for mass, and this is for distance. Next, this is moment of inertia is a rotational analogy of mass. What does this mean? Moment of inertia is rotational analogy of mass. Analogy means way of writing in rotational. We'll start from here. We'll be able for better understanding. So this is for linear and this is for rotational. In linear, the same things, okay? We know that displacement is what? This is S written here. What is this analogy? This word is called analogy. This is called linear analogy and this is called rotational analogy. Now in linear, what we use is S. In this we use theta, that is angular. Then for velocity we use V. Here we use W. For acceleration we use A. Here we use alpha. In order to produce in acceleration, here we use force F. Here we use torque, that is tau. Okay, so same thing what they are trying to say is, we'll see what does mass mean over here. So till here, this is the analogy. Now we'll see what is moment of inertia over here and here what is the relation. So we know that force is mass into acceleration. So just multiply by r on both the sides. Before that, I'll just tell you the relations. What is between this and this relation? Always S is equals to r theta. V is always equals to r omega. Acceleration is always equals to okay. So same way we'll see what is happening here. So we'll just try to multiply it by r on both the sides. This will be rf. This will be r into m to a. What is acceleration? R into alpha. So instead of acceleration, I'll use this is what for translational. We know that force is mass into acceleration. So I'm just trying to write in terms of rotational now. So what is alpha? This acceleration relation between this is r times alpha. Instead of A, I've just substituted here. So what is this going to happen? R into R will give me R square. Okay, I'll write it as M R square. There is alpha. What is R into F? Whenever there's a perpendicular, torque is always R into F. These are the relations, okay, between this and this. So this is nothing but your torque. And what is mr square? Well, just now we have seen. What is mr square? What is the product of mass into r square? Nothing but, this is nothing but inertia, no? What is the formula of inertia? mr square. I is nothing but mass into square of the distance. So this is I into alpha. So just try to relate. Force is mass into acceleration and torque is I into alpha. So what is this? M E, and this will be, what is that? M R square alpha. Force means torque, R this means this. So what is the M means? mr square. Okay, just try to relate this. Even without this, you just try to relate this. Force means alpha, okay, in rotational. Sorry, torque in rotational. Acceleration is nothing but, this is of linear and this is of rotational. So just comparing, so what will be M? M is nothing but inertia. So that's why mass is rotational analogy, or you can say inertia is rotational analogy of mass. So mass in linear is equals to inertia in rotational. How we say S is distance in linear, theta is the displacement in rotational, V is distance, this velocity in linear, omega is what? Angular velocity in rotational. Same way, this is acceleration for linear, acceleration for this. So mass is for linear, and what is equivalent of mass when you go into rotational? I. Okay, so right now mass in M means inertia I in rotation. So this is the equivalent of this. Okay, this is important to know. So in linear it is mass, in rotational it is called inertia. Next we'll see what is the kinetic energy. Kinetic energy of translation motion everybody knows. Or in linear motion is K is half mv square. We have always studied that. Till now we have studied only linear motion, no, in a straight line. So that was half mv square. This we already know. Now we have to calculate for what What is the same kinetic energy in rotational motion? I'm trying to calculate this. So for a rotating body, here we use V. For this, what we'll have to use omega, no? So for linear, it is V, and for rotational, it is omega, or W, whichever word you use. So V is, what is the relation between this and this? R omega. So for a system of particles we are referring, so directly I'll use I. This is for one particle, V is equals to R omega, but the whole thing, if it's spinning, for all the particles, V will be equals to R omega. So what is kinetic energy in translation motion? Of MI square. This is for translation. So put this equation 1 into value of Vi from equation 1 in equation 2. Because I want to write kinetic energy in terms of omega now. I don't want in terms of V. In terms of V, it is for translation. But I'm trying to calculate it for rotational. So I want in terms of omega. So instead of V, I'll put this. So here also I'll use I, because it is for all the particles. So half Mi, put this here, Ri, Rwi. This will be also I, know all the distances also. Everywhere I put I, because it is a square here, this will be square. So instead of Vi, I put this Ri omega I. Open up the bracket now, everything will get squared. The total kinetic energy, you can consider summation of all this, all the small i's, you can add them up. This is the total of all this. Okay, if we add all the summation, you'll get total kinetic energy of the whole body. So just put it here, half Mi Ri square. Okay, total kinetic energy is sum of all the ones where I is from 1 to n, all the n number of particles. If I add all the particles, I'll get the total kinetic energy of rotation of that particular body. Now half is a constant, I can always remove out. And for rotation with fixed axis, no, omega is always constant. Angular velocity will be constant. If you are keeping pen on one particular point of a regulator, you will not notice that half a rotation it will move at a different speed. Okay, you will never see that. For half a rotation, your fan will suddenly become slow, and half a rotation, it will become fast. Half part of the fan moving at a different speed. If you keep it at a fixed speed, it will move at that particular speed only. Until and unless you change the regulator, it will be constant. It will be moving at a constant angular velocity for a fixed rotation. Okay, for a fixed axis. So this is constant. So this will come out. So what remains is mi into ri square. And what is m into r square? M into r square is equals to I. That is a moment of inertia. So this is total inertia. So kinetic energy is half. Okay, overall this is constant. So you not even have to this. You can just generalize this, or you can say. So in general, kinetic energy will be omega ulta will write I first omega square. So here it is what? Half mv square in linear, and for rotational, this is for translational, and for rotational it is half I omega square. I told you all also what V means in rotation. V means omega, and what mass means in rotation, I. So it's the same thing. What is equivalent of mass in rotation? Inertia. Inertia is nothing but the rotational energy of mass. Omega is nothing but the rotational energy of velocity. So half mv square in linear and half I omega square in rotation. It's very easy to remember. If you know this half mv square, you know what is this. Mass means I in rotation and V means omega in rotation. So this is what? Kinetic energy of a body. Okay, I'll give some points based on that. Kinetic energy is independent of magnitude of angular velocity. Okay, it is independent of this because that is anyways constant. Depends on axis of rotation. Because inertia will change based on the axis. More the distance, more will be the inertia because it is mr square. So it is independent of omega but depends on the axis of rotation. And in case moment of inertia, for moment of inertia, I am not given this. It depends on mass of the body. What is I? mr square. Depends on the mass. Depends on shape and size. Obviously, because bigger the size, bigger will be the mass. Distribution of mass. Depends, no? How far is the particles from the main axis, because R1, R2, this will also change. Because R will change. Position of the axis. How far it is from the mass. The moment of inertia depends on all these things. So remember, more the distance, more will be the inertia. More the distance means distance of the body from the axis. More will be the inertia. Inertia is nothing but like the resistant force. It tries to keep you in the same position. Examples also in earlier when we studied inertia, when you're sitting in the bus, when the bus applies brake, you tend to remain as it is. Bus moves forward. That's why you tend to fall backward. But you try to keep the same position where you were sitting. When it applies brake, this is the one. So when it applies brake, bus actually moves backward. You tend to remain here. That's why you tend to fall forward. When apply brake means it stops. The bus stops, but you continue to move as per the bus. That's why you tend to move. So that is inertia. Trying to remain in the same position as the motion. Next is, I don't know if these are there for you. Earlier there should be big derivations of that. I don't think so. It's done for you all in the college. You let me know. But there are moment of inertias for different objects. Moment of inertia of different bodies. Suppose if we have a rod and all, you can always calculate based on where it is, the length. Like for example, one small one only I'll do. First one. Suppose if this is, I'll just give an example. If this is a rod, it means mass is at this point and mass is at this point. You want to calculate the moment of inertia due to these two masses. And this is the length, suppose. Okay, this is length. So this will be L by 2. And from here it would be L by 2. Center of mass would be here. So total mass, if you consider this plus this is M, this will be M by 2, this will be M by 2. If total mass is M, then half mass here you consider. Then moment of inertia is what? M1 R1 square, M2 R2. So as per that, this will be M by 2. Then this you have to calculate. From the center, this is the axis to be considered. To calculate, this will be ml square upon 4 you will get. So this is how we can calculate for different objects. For a circle, considering all the masses. So different shapes, direct, they have already derived, they have fixed derivations, moment of inertia for different kinds of bodies. So if it's there for you, I will just go through it. Just give and keep. If how to derive those is asked, then just let me know. First one. This will be the body. This is axis of rotation. This is moment of inertia. Okay, first one is thin rod. I'll draw the diagram here this side. If you have a thin rod, body is nothing but a thin rod. Axis is perpendicular to midpoint. This is a midpoint. And the answer is second one. A thin rod, but at the end is the axis. Perpendicular to rod at one end. Then moment of inertia is ml square by 3. This is the length of the rod. Third one, thin ring if you have. Axis is the diameter. Then moment of inertia after calculating you'll get 0.2. Fourth one, thin rod only, but axis is like this. Thin ring only. The tangent at the end. And the answer is 3 by 2 mr square. Fifth one, if you have a thin ring, this time it is perpendicular. This is perpendicular to the ring. Then the answer is mr square. If you have a circular disc, now this is a disc, okay? Means this is only outer, inner it is hollow. Disc means it will be full. one. Again, same thing, diameter is there. Mr square by 2. Seventh one, circular disc on it. It is axis is the tangent. Five upon 4 mr square. This is mr square upon 4 diameter. This is 4. This is perpendicular. Perpendicular to the disc. Then this is mr square by 2. Ninth one is a hollow cylinder. Hollow cylinder. Axis of the cylinder. That is mr square. Now this is solid cylinder. It is full packed. The whole mass. This is empty. This is hollow inside. This will be mr square by 2. And the last two. 11th one. Solid sphere. Sphere this is not disc. This is across the diameter. This is ulta. Mr square by 2 and this will be 5 by 4. Sorry, 2 by 5 mr square. Oh, this hollow is left. No, 1 second. Hollow will be hollow. One will, the diameter is left. Diameter, I think it is 2 by 3 mr square. 14th is with the tangent. This hollow sphere. We have a team. It's like a hollow ball. A balloon you can consider like a spherical balloon with a tangent here. You try to calculate moment of inertia across this axis. Then hollow sphere only. But now I'm calculating it along the tangent. Then I think we should get 7 upon 5 mr square. So this means now just trying to tell you that various bodies will have various moment of inertia based on where your axis is. Various shapes have different moment of inertia. Next we'll see what is radius of gyration. Small topic. Then this I forgot to download the image. But just consider, suppose this is a giant wheel and people are there at various places. Okay. Now where do you think the center of mass will be? Definitely at this point. Okay. So whatever is the, you try to calculate for every particular. Now if you are sitting here, for you the radius of gyration would be the distance from the word, here we'll use the letter K. The distance from the main center of mass. Okay. Or distance of, this is the axis now, suppose. The distance from the axis of rotation to the point is assumed where the mass is assumed to be concentrated. So where mass is concentrated means basically the distance from the center of mass. Distance. What is the radius of gyration? Distance from the axis of rotation. We are here, and this would be the distance. At which mass of the body is assumed to be concentrated. It is denoted by K. I'll draw a diagram. Suppose you have this, and this is your reference, and this is your mass M1, M2, different spots there, M2, maybe M3 is here, M4 is here. So this will be R1 from the main reference axis. This is M2. This will be M3. This will be M2. Basically, it's the whole, this is only one particular body. Okay. So finally, it would be like a center of mass only here. So from the main axis, it would, if your center of mass is lying here, no, consider it's the entire body after adding all this, it's here. So one particular, this would be K like. We have to consider thinking all of this. So what is moment of inertia? Moment of inertia for all these particles? We are trying to derive the formula for K. Small one it is. X is I is what? mr square. We know that. I is always m into the distance. Sorry, this is R2, this is R3, and this is R4. The distance from here to here. Now we have to add all of them. There are n number of particles. I is what? m1 r1 square, m2 r2 square, m3 r3 square, so on up till mn. Okay. Now these are particular masses of all the system of particles. How many number of particles? Number of particles are n of them. So I'll just multiply and divide this. Okay, this particular thing. Suppose if I'm taking m as common, when I can take n common, if for n number of particles. R1 square. If m is mass of one particle, so mass of n number of particles will be m into n. So if this is 1 kg. So if I have 100 particles, I'll have to multiply it by 100. If I'm multiplying it by 100 means the same thing I have to divide also by the same number. Balance it out. And this is nothing but a total mass. So it's like how 1 kg into 100 kg will give me the 100 particles will give me the whole thing 100 kg. There's nothing but total mass of the body. And there's a capital M for that. Where M into N is total mass of body. So what is this? Nothing but the distance only. So if K is the radius, of gyration, means what? From the main mass till this, if I'm using, suppose this is a M, and from here to here, if it is K, I'm using the letter K instead of R. For radius of gyration, we just use the letter K instead of R. So if it is there, then what you know? It's nothing but M K square. Where K, just compare it with this equation. So K square is nothing but R1 square, R2 square, R3 square till Rn square upon N. This is equals to this. So K is root of square of all the distances upon the total number of particles. So this is the formula for radius of gyration. So it depends on axis of rotation, how far it is, and distribution of mass, or distribution of particles or mass along the about the axis. So this is all about radius of gyration. What is radius of gyration? Nothing but the distance from the main axis to the mass where it is assumed to be concentrated, basically at the center of mass. And the letter indicated is K instead of R. So it is summation of all the radius square. Let's stop here.